Alright guys, today's goal, the learner will understand polar equations of conics. We're going to revisit eccentricity. We're going to be writing polar equations for conics, analyzing polar equations of conics, and orbits revisited. Okay? So, and why? You will learn the approach to conics used by astronomers. So, focus directrix definition for conic section. A conic section is a set of all points in a plane whose distance from a particular point, the focus, and a particular point line, the directrix, in the plane have a constant ratio. We assume that the focus does not lie on the directrix. We've talked about these things. Now, a conic section in a polar plane. Okay, so polar plane is different. Remember the distance from the focus and directrix always used to be the same? Well, now it's not the same, but it's the same ratio. Okay, so if you move over, if you were to go here, or if you were to go here to here, those are the same ratios, okay? Same thing goes here. Okay? So the focus at the pole. So this is your r distance. And this is your k minus r cosine. You'll see when we get to the equation. But these are the pieces. These are how they're formed. And see the directrix, x equals k. Alright. Three types of conics for r equals k times e the eccentric, 1 plus e the eccentric cosine theta. The ellipse is when the eccentricity is less than 1. The parabola is when the eccentricity equals 1. And the hyperbola is when the eccentricity is greater than 1. Polar equations for conics. So here are four different types. Four standard orientations of a conic in the polar plane are as follows. So if you have the r equals, directrix is x equals k, they're curved like these. X equals negative k, they're curved like this. If you go y equals positive k, opens down. Y equals negative k, opens up. Okay? Or curves up. Alright, so let's take a look at some examples of what to do now. So given that the focus is at the pole, write the polar equation for the conic with eccentricity 4/5 and directrix x equals 3. Okay, so do you see here? We have x equals 3, so x equals positive k. So that's why we're going to be using this form. So let's take a look. So now that we have it identified, we're using this. We know E equals 4/5 and k equals 3. So let's just plug these in. R equals 3 times 4/5 divided by 1 plus 4/5 cosine theta. Now let's double check, make sure we didn't miss anything. Nope. Now, so then we get R equals 12/5 over 1 plus 4/5 cosine of theta. But you don't want fractions like this. So multiply the top by 5 and the bottom by 5. So you get 12 over 5 plus 4 cosine theta equals R. So there is our polar equation. And you can check and look at the graph at this by putting it into your calculator. So if you have your calculator, get it out, make polar equation, and enter this equation in. And if you did that, you're going to see that it looks something approximately like this. Now see, yes, they had the curve going this direction, but it's not a parabola. It's just telling you the direction that that bend would be making. Okay? All right, let's look at another example here. All right, it says determine the eccentricity, the type of conic, and the directrix. Okay, so we're looking for all of these. We need to figure out less than 1, equals 1, greater than 1. Well, here's the thing. The standard form, this needs to equal 1. So you need to divide the top by 3 and each piece of the bottom by 3. So you would get 2 over 1 plus 2/3 cosine theta. So we now know E equals 2/3. So we know that this is an ellipse. Okay? So now we need to find the directrix. So we need K. Well, we know 2 is equal to K times E. Well, we know E is 2/3. So multiply by the reciprocal and you get K equals 3. So the directrix, so it's an ellipse. The eccentricity is 2/3. So one solution, 2, and the directrix is x equals 3. Okay? So I will see you guys tomorrow.